5-1 for work and do on the worksheet. Worksheet number 1, 3, and 4. If you want to try and do number 2, you can. But I might do extra work. But if you want to do 2 instead of 3, you could do that. You could do 1, 2. 2 is a little bit involves gravity a little bit. I'm going to see if you can figure that. I'm having some technical problems, and I need printer ink, and my computer's overheating. But I'm going to try to do this right here from looking at my computer. Okay, this part about work. This is a section we're not going to spend too long. We're going to see. I don't know if I'm going to go through the entire chapter or not, but we'll see. 5-1. You got to have some kind of overview about what is meant by this. What in the world is work? Okay, in physics, work does not mean like a job. It does not mean like your homework you're doing. Work. You got to work on this. Do yard work. Well, actually, yard work. That's pretty good. You'll see in a minute. But work involves, and it says, look on your paper right there, the movement of an object through a distance while a force parallel to the direction of motion is being applied to it. A force is, I might even say, while a constant force parallel to the direction of motion is being applied to it, acting on it. Okay, the movement of an object through a distance. Why in the world do we have a crazy little word like that? Well, we'll be spending some time doing some problems in lessons. This definition will come out a lot better. But basically, here's an easy way to kind of remember it, or to think about this. If they've got a heavy rock right there, it weighs 25 kilograms, and we have our little friend Lily, and there she is, and she's gonna push this thing. She's with all her force, all her might. She's gonna push that rock and move it along. Let's just say she moved it, and how about she already moved it, and she'd been walking, and let's say it started here, and it went to there, okay? And went from there to there. Okay, she moved this rock. She was standing back here behind the chalkboard. You couldn't see her, and she pushed it from this point all the way to there. She was applying a force parallel to the direction of motion, and she was causing this thing to move. Now, work requires energy, obviously, and you're going to see that work and energy are both really the subjects of this chapter, this unit. But it takes energy to do work. When you have energy and it's correctly expelled, you're able to cause motion. I think I told you this already, or maybe earlier in an earlier chapter. If you can do anything to influence the state of motion of another object, then you had to put a force on it, and you had to do work on it. I think it's pretty safe. I think that's pretty safe to say that. So that means if an object was not moving and you caused it motion by putting a force on it and cause it to move, that's one. You can take an object at rest, you start it moving, or an object is moving and you stop it. Okay, or an object is moving and you change the direction of it. Okay, whatever. Volleyball is the best example of this all the way, because sometimes you serve it, it stopped and you put it in motion. Sometimes you obviously completely change the direction of motion the entire time, and then sometimes I guess if the whistle blows, then you catch the ball, you stop it. Okay, so all of that. Now, I want to make sure I can see my screen. Okay, so here's the equation for work. You'll find this pretty easy. And then we'll spend a little time with class as well trying to understand what exactly it means. It's the force parallel to the direction of motion times the distance. That's called work. The unit for work is called joules, capital J, Joule. If you took chemistry, you may have seen joule. It's the last name of someone used for energy. And as I told you, you're most familiar with calories in the English and British imperial system that we use in this country. But calorie and joule are just like meters and yards. Yards are in Britain. Meters are the metric system. Okay, well, joule is the metric system and calorie is the English system. Okay, all right. And so in the same way you can have work done, you can also have net work done. And we'll talk about that later. Net work is the sum, just like net force, it's the sum of all the works done on an object. So let's just say that she's pushing it, and her name is Lily A. And you also have friction here. Friction could be force B, okay? So you might even have somebody else pushing. It could be C. So all the forces that are parallel to motion, they can be pushing it, acting for it, or against it. each individual force can do work. So work, object A plus the work vector of B, the friction, plus etc. If there's C, D, I usually put A, B, C, but I guess I ran out of space. Or another way to calculate net work done is the net force times the distance. The net parallel force, I guess you might say, times the distance. So FD net. So that same equation, F parallel net, will give you the net work. Okay. All right. So here we go. Let me try a little bit of a calculation here. And it looks like letter A says, okay, and we got our little, actually we got Lily and Spot. You know what? I can just take that picture and turn it into this. It says, Spot is pushing a box on the floor with a 275 Newton force. So I'll put our little friend, Spot. Uh-oh, his feet have to be up there. Oh no, his arms are going to look really weird. Oh, he's going to look really strange. Oh well, put his little tail, his feet here. I don't know. His arms are looking weird. Oh well, that's going to be Spot for now. I got to get this done. Okay, Spot is pushing a box on the floor with a 275 Newton force east. I guess I got him drawn backwards, but oh well. But he's pushing with a force of 275. She's pushing with a force of 35. So it was the other way around in my picture, but oh well. It doesn't matter. All you got to do is this. We'll let that be east and that be west. Okay. Now, the box moves 6 meters east. So Spot wins out. He's pushing 275. She's only 35. It's going to move that way. We'll let that way be positive and that way be negative. It's kind of good because it's opposite of how we think sometimes. It'll show you. You can always do this in your picture. I just wanted to save a little bit of time. All right, what is the work done by Spot? Okay, so A, number 1, the work by, if I want to say Spot, the work is equal to the parallel force times the distance. So he's putting 275 newtons, and the distance it went is 6 meters. Now, when I multiply that, 275 times 6, oh, I am so sorry. You know what? The D is the displacement, not the distance. Well, it is the distance in this problem, but we need to make sure we know that it's positive, okay? And it is a positive 6, okay? So we got that right. Somewhere you have to put a sign, like the force is positive and the displacement was positive 6. You can put it in either one actually, but don't put it on both of them. Don't put it like negative, for example. Don't do that. So 275 times 6, 1650. Now notice the unit would be NM, Newton meter. Well, we have an abbreviation. We turn Newton meter into J, joule. So a joule means when a force has been applied to move an object 1 meter in distance. So when a force is being applied as an object moves 1 meter in distance, okay, per each meter. So 1650 Newton meters. Well, they call it Newton meters, I guess. So each, oh well, just understand that that's joule. I'm trying to say Newton meter. What a strange thing. Joule is a better way to say it. All right, for 2, we're going to do for Lily. So look at the force done. The work by Lily would equal the force that Lily applies times the displacement. So you can say hers is negative 35 newtons. I guess it makes more sense to put the force negative. And then negative 35, but notice, oh no, you would put the sign in there. Even though she pushes negative 35 in this direction, it's moving against her. So she's going backwards as it pushes. She's pushing it, but she's slowing it down. If she moved out of the way, Spot would move it faster. So her 35 is contributing something. She's saving the box or whatever, tug of war, or whatever game they're playing here. So it's negative 35 hers, but it's still a positive 6. So I told you a moment ago, I said only one needs it. Well, they both should have it. I mean, it's going to be positive 6 in both cases. All right, so 210 joules would be the work done by Lily. Oh, negative 210. All right, So, let's see the next question. I have to look at my notes on the computer screen. Calculate the net work done on the box. So, the net work means just add those together. The net work equals the work by Lily plus the work by Spot. If you want to do it that way. Lily's work was, well, I went backwards, negative 210 plus Spot was positive 1650. They're both joules, okay? So 1650 minus 210 is 1440 joules. That's pretty much it. Now, if there had been friction involved here, like if we had said, oh, the box weighs, 200 kilograms and mu k equals 0.300. Well, then remember, you can calculate the friction force. So from last chapter, that kind of continues a little bit. Find the normal force, the weight, and the normal force will be the same here. Multiply by mu k, get the friction force. Then the friction force times the distance will give you the work done by friction. You're going to see that in at least one problem. Let me see what else you might see. On the homework, let me look at it real quick. I put number 1, 3, and 4. Number 1 is a lot like, the same as what I just did. Number 3, 3 I put friction in there, and it's not so hard to do that. Okay, and then number 4 is a crazy problem. I do like number 2, but I guess I'd rather just hold back on that one for now. So, because I want you just to focus on these. But I will just tell you one little quick thing. Okay, if there had been friction here, I'll just show you. Let's do what I just said. Mu k equals 0.300. If there were friction, if you want to add this, if there were friction, okay, well, that's going to change things. Well, first I would have to do this. Friction force is the normal force times the times mu k. I'm sorry, I got it backwards. The constant times the normal force. So the normal force would equal the weight here. So if it's 200 kilograms times 9.81 meter per second squared, for the weight, acceleration of gravity. So that's going to be 1960 newtons. 1960 newtons. Yeah, 1960 newtons. So if the weight is 1960 newtons, the normal force will also equal, or how about this? The weight is negative 1960, and normal force is 1960. So they're the same thing. Remember I told you, that's not going to matter. Your weight force is here. Your normal force will be the one lifting up. We'll let the normal force be positive and let that one be negative. So mu k would be 0.300 if there was a friction force of 0.300. 300 times 1960. And so, we've got a big problem. I'm going to have to, again, my example, it can't be 0.300. How about 0.0300? That's more like it. 0.300 times 1960. I got to make my problem different. 58.8, that's better. 58.8 newtons. Let me explain why in a minute. Okay, I just made this up because you're going to see a worksheet problem. If you don't want to do this, if you don't want to see this part, you can just go to the worksheet, but this will help you. If there's friction, I will tell you mu k equals, like I'm telling you, make it 0.0300. Because if it were 0.300, the object wouldn't be able to move. The friction would have been too great. So that's why I made my example up and it wasn't good. So 0.300 is 58.8 newtons. Now, which way does the friction force act? It always acts opposite direction of motion. So he's pushing it 275. She's resisting it. Well, friction will also be resisting it that way. So now, if I want to get the net work, just remember that friction force is negative. Okay? I'm sorry, it's positive here, because I let that be positive and that be negative. His is pushing, oh no, I'm sorry, it is negative. Oh, what am I? Okay, yes, going that way. Friction is negative, yeah. Friction is negative. Lily's work is also negative. I erased it. And then Spot's work is positive, okay? So to get the work by friction, it's just going to be the friction force times the distance. So negative 58.8 times 6. It's going to be negative 352.8 joules. negative 352.8 joules, the work by friction. So we got the work by Spot, the work by Lily I erased. What was it, 35 times 6? It was 210. So now I'd have to say the net work would now equal the work by Spot plus work of Lily plus the work of friction. This is just to help you with the last problem in case it pops up. So Spot was positive 275. Lily is negative, what did we say, 35 times 6, 210, joules. And friction will be negative 352.8 joules. Is that right? That still might be too much, isn't it? 275, let me see. No, wait, 275 minus 210 minus 352.8. I get negative 287 or 288. You know what? This was not a great example I made up because it looks like my friction is still too much. Oh, no, wait. The friction force wasn't too much, was it? No. 58, 35. Oh, wait a minute. I know what I did wrong. Spot was 1650. Okay. Crazy Vela. All right. He was 1650. I'm sorry about that. Lily was negative 210. And then I know some of you were yelling at me, Vela, could you hear me? Could you hear me? Oh, I didn't. Okay. 1650, negative 210, negative. Okay, let me get this right. 1650 minus 210 minus 352.8. It's 1090 joules. And it's positive. It should be positive. That's the right answer. Okay, sorry. Well, anyway, if you see friction, just remember there might be a third force, and it will be opposite direction of motion. All right, thanks a lot, you guys. Hope that didn't get crazy at the end, but I'll try to clear it up in class too.